So we'll keep moving forward and we'll do our other regression models. So the next one we'll run, we can kind of reset, actually I'm going to reset the whole test. And then our dependent variable is still going to be batting averages. For this particular test, we're going to do all of our variables, or we want to consider all of our variables, and we're going to use the forward selection method. Okay, so I'll stick this here, we'll get to the output, and then I'll show you how the forward selection method determines which variables get included. For our statistics, we'll just make sure we have all of the same boxes checked as our previous examples. Our plots will be the same, and we'll generate our output. Let me get rid of things I don't need in here. So again, log, notes. I will change this title to batting averages, and this will be my forward method. Okay. And when we look at this, we can see variables entered and removed. We ended up creating 3 models. So in the first model, runs scored was entered. Model 2, strikeouts was added. And model 3, doubles was added. And you can see the forward method is listed in the method column. And the criterion is that the probability of F is less than or equal to 0.05. I know that's kind of staggered, but that's what the criteria is. So I'm going to pull up the flowchart to help make sense of this a little bit more. So in a forward selection method, the goal of the regression is to determine if the addition of a given independent variable significantly increases R-squared. Because again, whenever we choose a model or a final model, usually it's going to be based on the fact that we have maximized R-squared as much as possible, meaning that the percentage of the the percentage of the dependent variable that we've predicted is as high as we can get it with the independent variables that we've included in our model. So maximizing R-squared is kind of the goal for any regression. But we want to see if R-squared is increased significantly. So in a forward selection method, we start with no variables in the regression. So that's kind of like a pseudo model 1, if you will. This one never shows up in, well, I won't say never, but it doesn't really show up in our output. And then what we do in order to figure out what the first variable that's added, which is technically model 1 that we see in the output, that's determined by the independent variable that has the largest correlation coefficient. So just looking at the R value between our dependent variable and any of our independent variables. The one with the largest R gets thrown into the model first. Obviously, that's going to increase our R-squared value from 0 to whatever we're adding. So we have significantly added to our R-squared change. Therefore, if we follow this flowchart, right, does R-squared change significantly? P-value signals yes. So we keep the independent variable in the equation, and then we just keep adding to it. So let's say that we have put in our first variable that has the highest or strongest correlation. We've increased R-squared significantly, so we decide to add it, And then we end up with an equation that has a single independent variable with our y-intercept and our dependent variable that we're trying to predict. We then go back and consult our R values, okay? And then we add the independent variable, or the next predictor variable that we've decided to include in our analysis, that increases R squared the most. So whichever variable that is, we throw it into the model. We say, does R squared change significantly? If it does change significantly, then we add it, right? And so then this is an example that we've added another independent variable to our regression equation. Now, what happens if we follow that procedure again? So picking the remaining predicting variables or predictor variables that increase R squared the most. We choose one of those variables, throw it in the regression equation, and then see if R squared has changed significantly. When we do not see a significant increase in R squared, we actually end up taking that variable out, because again, the goal of our regression is to maximize R squared. So if we're putting it in a variable that doesn't really significantly contribute to the regression equation, we don't really decide that we need it, right? So I've indicated that that independent variable, or that predictive variable that should have been added in this last model, was going to be x3, or variable 3. Okay, and because it didn't significantly change R squared, we decided to remove it, and we stuck with the equation that we had in the original, or the model previous to this one. So this pseudo model actually isn't included in the SPSS output, and this first model isn't really included in the SPSS output. Okay, so if we go back to the results of our forward selection, we see that our model summary shows we've got 3 models, and if we consult our caption down here, we can see which variables were included in those models. We have an R squared for each of our models, expressing the shared variance between the independent variables included and the dependent variable batting average. We can see the R squared change, right? So in this case, runs scored was the first variable added. Obviously, we're going to have a significant change in R squared. So then we chose the variable that increased R squared the most, and we added that one in next. That would have been strikeouts, because that was the next variable entered. We then said, did this change R squared significantly? We see a p-value less than 0.05, so yes, adding strikeouts significantly improved our model. So then we did the cycle again. We said, ooh, our percent doubles adds to R squared the most, so we'll put that in there. We noticed we also had a significant increase in our R squared, so we kept it in. Right, but we had other variables. If I scroll down, we can see the excluded ones, right? So this last model here shows that triples and home runs didn't really make the cut, right? So basically what this means is that when after we added strikeouts, or after we added doubles to our last model, maybe we said, oh, triples maybe increases R squared the most, and we tried sticking that in to the regression equation, but it did not significantly increase R squared. Therefore, it wasn't really contributing to the regression equation that much, so we took it back out, right? And again, that pseudo model, model number 4, isn't included in the output. So I just wanted to note that's where it is. But these two were excluded because they didn't significantly contribute to the prediction of batting averages. Okay. So that's how we can determine or interpret our f change, or our p-values for our r-squared change. We can evaluate our ANOVA pretty similarly to our previous examples, and we can create our equation using the final model in our output. So going back to our Excel spreadsheet, we can say that our constant is 0.169 plus 0.575 multiplied by runs scored, so I'll just put RS as a placeholder. And then our next B coefficient is minus 0.264 times strikeouts, so I'll put SO for that one. And then last but not least, we are adding 1.119 times our doubles, so I'll just put D for that one so I know what it stands for. Okay, I now have my equation from my forward regression. Similar to our previous examples, you guys could check the normality plots. This is a much better example of a homoscedastic set of data. So again, anytime you run your analyses, you want to check your assumptions first. Our Durbin-Watson statistic looks good. Our collinearity statistics look good based on our criteria that we've discussed in previous examples. So I would say that we've probably met our assumptions pretty well. We've got an equation that we can now use, and then our next example would be our backward regression. So let's go ahead and set that up. In terms of the setup, everything is going to be the same. Instead of forward though, we're going to choose backward and then just press OK, because everything should have been saved from the previous run through. I'm going to change my title. And this one will be batting averages backward method. I'll change this back to the font size it's supposed to be. Here we go. Alright, and then in this type of model, you can see that things look a little bit different. So in forward selection, we start with no variables in the model, and then we add them in one by one based on the criteria that we are increasing or significantly increasing R-squared. The backward elimination model is of a similar idea, but we start instead with all of the variables in the model, and then we take them out one by one to see if R-squared decreases significantly. Okay, so if we look at the criterion over here, it's the probability of F to remove greater than or equal to 0.1. Really what we're looking at is, do we have a significant decrease in our R-squared value? So I can pull up our flowcharts just so you get an idea. The way that this works is, again, pretty similar. It's just like a forward selection flipped around. So the goal is still to maximize R-squared. So as we're taking away, obviously if we have all of our variables in, R-squared is going to be as big as it's going to be. But what we need to figure out is take out variables that reduce R-squared the least, and then evaluate if the R-squared change is significant or not if we have a significant decrease in r squared, we need to put the variable back into the equation. But if r squared is not reduced significantly, then we can keep removing variables from the equation until we find our optimal equation where we're maximizing r squared while also only considering variables that are significantly contributing to r squared. So an example here is that we put all of our variables into our equation to start, and then we remove the variables that decrease r squared the least. If there's no significant change in r squared, we remove the variable because it was not significantly contributing to the regression equation. On the flip side, if we remove a variable and it does decrease r squared significantly, then we need to put that variable back into the equation. Okay. So looking at our model summary, we can kind of figure this out a little bit easier. We can see in our first model, all of our variables are in there: strikeouts, doubles, home runs, triples, runs scored. Okay, so r squared is going to be as large as it can be with all of the variables in there. We can then see by looking at this caption down here that triples is the variable that's missing from the second model. So that means that triples reduced r squared the least, and then when we removed it, we said, was r squared changed significantly? And in the second model, we see that the f change, or our r squared change, is greater than 0.05, or the p-value is greater than 0.05, which means we did not significantly decrease r squared. So that indicates that triples really didn't significantly contribute to our regression model. If we then go to model 3, we can see that the variable that was removed was home runs. Okay. And then we assessed, when we remove home runs, does that reduce r squared significantly? It was determined no, because 0.205 is greater than 0.05. So we decided, well, if home runs doesn't reduce r squared significantly, then we don't really need it in our regression equation because it's not significantly contributing to the prediction of batting average. Okay, so then we were left with our third model, which basically just has strikeouts, doubles, and runs scored. And the reason why we were left with this is if we added an extra model down here and tried taking any one of these variables out, likely what happened is that the removal of one of these variables caused a significant decrease in r squared. Thus, the regression model was like, yikes, we need to put that variable back in so we keep r squared as high as possible. Okay, and that's the model we ended up with. Okay, we can see Durbin-Watson statistic is pretty close to 2, so I'd say we've got independence of observations. We can interpret our ANOVA. In other words, this worked pretty well, or the final model worked pretty well in determining our batting averages. For our coefficients, we can type in our final equation, which actually is identical, for the most part, to our forward regression. This doesn't actually always happen, so that's a nice refreshing occurrence. But I'll put these in one by one. Same way that we've done all of our other examples. And the last one is minus 0.264 times our strikeouts. Okay, it is important that you match the appropriate independent variable with the B coefficient. Okay, so you'll notice that we have the same coefficients, but the order of the variables is different in this equation than it is in the forward regression. So it's very important you don't get your variables mixed up. Okay. If we look at our collinearity statistics, all of those look pretty good. It doesn't seem, or we don't seem to have any outliers in this data set, so that's good since we don't have any case-wise diagnostics popping up. By evaluation of our histogram and our PP plot, those both look relatively normal in terms of our residuals distribution. And then our scatter plot at the end, we don't really see a major pattern in the dots, so that would suggest we have homoscedasticity in our data. Okay. So again, usually you'll want to check your assumptions before you continue with your analysis, but because we're not really making any adjustments, regardless if we have met assumptions or not, we just kind of go with the flow. Okay. From here, I did want to pull up the answer sheet. So in this section, you've got some questions to answer up here that are related to what comes in the output. And we've gone through examples of all of these, so you should be able to answer those ones. The regression equations you're going to input here are the same ones we created in our Excel spreadsheet. And then question number 10 is asking which model accounts for the largest amount of variation in batting averages. Okay, and you're going to use calculated values to support your answers. So you have to decide for yourself, I won't tell you the answer, what looks at the percentage of variation in batting averages, right, based on variables that are included in a model. So figure out what value I'm talking about, and then compare your models to see which one accounts for the most variation in batting averages. I then want you guys to list the p-values and the interpretations for significance of each model. Okay, so if we're looking at the model in its entirety, that should be a hint that points you towards the correct table in the output, which we have discussed already in previous examples. And then the last one that I wanted to give you guys is what is the 95% confidence interval for the true linear relationship be between, and I forgot to fill in the rest of this now that I look at it. So let's make a decision that we want to look at the confidence interval. Let's use the last regression that we ran. And we're gonna look at the confidence interval for doubles in Model 3. Okay, so I'll just add that in here. We'll say between percent doubles and batting averages. For the backward method, since that was the last one we did. And then, like I said in the lecture, default, always look at the last model in your output. So this will be specifically for Model 3. Right, but we can observe what the confidence interval is. So basically you're just going to list that as your answer. You're welcome. Okay. Let me minimize those. That should be it for this data set. We are going to use some of this calculated information in our practice 3, so I will leave this video where we are, and I'll see you in the next one.